Hey guys, so welcome to your lesson on polyatomic ions. As always, your guided notes are linked in your assignment, and if you can't print them out, not a big deal. You guys will be taking notes on page 44 of your interactive notebook. So these are for your polyatomic ions and covalent bonding. So let's start by breaking down what is a polyatomic ion. So poly means many, so we're going to be talking about many, so more than one. And then atomic is atom. So a polyatomic ion is going to be an ion that has more than one type of atom in it. So basically what it is when there are two or more elements combined to make one ion. Now remember, an ion varies in its charge, right? In the electron. So it's either got, a negative charge or a positive charge on it. So we're still going to be dealing with charges here. It's just instead of one element, we're going to be looking at multiple elements. So these can be a cation or an anion. Remember, cations are positive, so they've lost electrons, and then anions are negative, so they've gained electrons. So the example that we're going to be looking at here is ammonium. And ammonium is a polyatomic ion that typically has a charge of -1. Okay, so the charge is given to the entire group of elements as a whole. So the charge doesn't apply to just the nitrogen or the 4 hydrogens. It applies to the entire compound itself. Okay, so that -1 goes with the ion, the NH4, and it goes at the top. So we're going to put our NH4 in parentheses, and we're going to put the charge as a superscript outside the parentheses. You never change any elements or subscripts in the polyatomic ion. So if we're talking about polyatomics, you want to keep the atoms the same, the elements the same. We're not going to change the nitrogen or the hydrogen. We were really just looking at the charges, okay? So ammonium will always be NH4. Now here are your common polyatomic ions. These are the ones that you're going to be working with, but you don't have to memorize them. Okay, so there are the names of the polyatomic ions, and it also tells you the typical charges of them. So like ammonium, right there at the top is NH4, and it's got a +1 charge. Now you guys should have these in your purple reference tables, but I will also post up another image of them, and I think it would be a great idea for you to actually record them in your spiral bound index cards as well. Now, I don't know what testing is going to look like this year. I know that the state has put in a waiver to actually have you guys not take your state final. But if you do wind up taking it, the polyatomic ions are always provided on the final exam, so they're in your reference table. So no, you don't have to memorize them. But it's going to be important that you can look at them and reference them because you're going to need to get these charges. So just like our crisscross method for our ionic bonds, there's a crisscross method for our polyatomic ions. And we're basically going to follow the same steps. We just have to make sure we understand where our ions are. So the example we're going to look at is magnesium nitrate. Okay, step 1, we're going to write the symbol for each element. Magnesium is Mg, and then nitrate is NO3. How do we know that nitrate is NO3? You have the reference table of your polyatomic ions. You just have to find it on the table. Step 2, you write the charge for each. We know that magnesium is going to be donating an electron based on its position in the periodic table. So it's in group 2, so it will be donating 2 electrons, so it's got a 2+ charge. And then based on the table referenced, so your reference table with your polyatomic ions, we know that nitrate, or NO3, typically has a 1- charge, okay? Then we're going to crisscross the charge to the opposite element. Okay, so remember that lasso method or the crisscross method. We're going to pull this 2+ from the magnesium over to our nitrate, and we're going to pull the 1- from our nitrate over to our magnesium. Then we're going to draw out the charge, but we are going to keep our number. Okay, so this becomes MgNO3 2. Okay, so we keep the polyatomic, right? So our nitrate stays in its parentheses, and then the subscript from this 2+ charge that we crisscrossed over it goes outside the parentheses. Okay, remember, we do not change the elements or the numbers inside our polyatomic, so inside the parentheses. The subscript now goes on the outside. Okay, so that means for this to even out, right? Because remember, our ions have to be, our ionic compounds, they're neutral. The magnesium, we would need 1 atom of magnesium, and we would need 2 of the polyatomic nitrates. Okay, so we've done ionic, we've done polyatomics. Now let's look at covalent bonds. A covalent bond is the sharing of electrons between 2 nonmetals. Okay, so remember, ionic bonds are between a metal and a nonmetal. Covalent bonds are between 2 nonmetals. So these nonmetals can be anions or both anions, okay, because they are nonmetals. So they're going to be on the right-hand side of our periodic table. They're going to tend to take on electrons, so they will be negative. So they'll share charges, so have the same charges, and the charges do not equal 0, okay, because these are covalent bonds. Because they share the same charges, they're not going to be equal to 0, and they're going to form a molecule. Okay, so covalent bonds make molecular compounds. Okay, so when we talk about molecular compounds, those are also from covalent bonds. So the goal is still the same. We saw with our ionic bonds that an electron is donated. Here, we're still going to try to attain stability. We're still going to want 8 valence electrons in our outermost shell. It's just going to be done in a different way. Instead of one element donating their electrons to another, we're going to have some sharing going on. Okay, so atoms are just going to achieve it differently. So the first example we're going to look at are 2 atoms of chlorine. Okay, so how will 2 chlorine atoms react? Now, chlorine, it's in group 17 or 7A of our periodic table, so there are 7 valence electrons, and you can see that from the Lewis dot structures here. So how are these guys going to bond if they're going to make a covalent bond and they're going to share? So let's look. Okay, each chlorine atom does want to gain an electron to achieve an octet, right? Now, how are they going to do this? What can they do to achieve it? They can share their unpaired electrons. So instead of donating it to each other, they're just going to share it. They're going to come together and they're going to share it. So here they go. Oh, that looks nice. It looks like you got something that I want a little bit of. Okay, okay. There we go. So now, see, this original electron belonged to this chlorine. And then this electron belonged to this chlorine on the left. Well, now they've come together and they've formed a covalent bond and they are sharing the bond. Now this chlorine on the right-hand side has a full octet. Chlorine on the left also has a full octet because they are sharing electrons, but they still technically have 8 electrons in their outermost shell. They're happy. They're in a noble gas configuration. Okay, so this octet is achieved by each atom sharing the electron pair in the middle. Okay, so this is the pair that's shared right in the middle here. So the electron pair that you're actually sharing in a covalent bond is known as the bonding pair. So the bonding pair is what is actually shared. So there are 3 types of bonding pairs. There are single bonds, which is when you have a lone pair that's shared. And they each need 1 valence electron to be stable. Double, so if you have a double bond, you have 2 lone pairs shared, and that's like with oxygen, and I'm going to show that to you in just a second. And then a triple, you have 3 lone pairs shared, like with phosphorus, where each one needs 3 valence electrons to be stable. Okay, so with chlorine, they were each just missing 1, so they just had to make 1 bond, where they had to share their lone pair electrons. With oxygen, we're going to see is a little bit different because oxygen needs 2 electrons to be happy, so they need to share 2 of their lone pairs. Okay, so with chlorine, again, chlorine only needed 1, so they had a single bonding pair. All right, this is a single bond. Okay, if we look at single bonds, they are abbreviated with just a single dash. So if we were to see this in like a Lewis dot structure or something, if we were to see this on paper, this dash line would represent that these 2 chlorine atoms are sharing 1 bonding pair. Okay, 1 pair of lone electrons. So normally in the final structure, the valence electrons are not actually drawn, so you don't see them as two dots, you just see them as a bond. So then the formula for this molecule would be Cl2 because you've got 2 molecules of chlorine. Now let's look at oxygen. So oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Okay, so these are 2 molecules of oxygen, each with 6 valence electrons. They want 8. Okay, so they each want 2 electrons to fill their outermost shell. So conveniently, right, these guys right here can pair, and then these guys right here can pair as well. Okay, and let's see what happens. Okay, so we're going to make these covalent bonds. Okay, oxygen atoms are highly electronegative, so they do want electrons. Okay, so these guys are going to come together just like our chlorine did, and boom, they are going to share their electrons. Okay, so both of these electron pairs are shared now. Now, see what happened here. We had our electrons on each of our oxygens kind of shift around a little bit, and now they're sharing their pairs in the middle. Okay, so their pairs are being shared in the middle. They're bonded here. Now here's 2, 4, 6. The 8 is going to look a little bit different because the 8 are going to come from these 2 electrons over here. You're not going to see it on the bottom like you normally would in a full Lewis dot structure. So this is just going to signify a double bond. Okay, so both the electrons are shared. There's one, there's one. So they're each sharing their electrons, right? They've got 6 here, plus the 2 that's shared gives you the full octet. 6 here, plus the 2 shared give you the full octet. Both these oxygens are happy, right? But here you've got 2 bonding pairs. The first one's here, and then the second one is below. So this is a double bond. So oxygen will make a double bond with another molecule of oxygen. Okay, and just like with our single bond, our double bonds are going to be represented by 2 dashes rather than the actual electrons themselves. Okay, so that's it. So at this point, we have been through ionic bonds, we've been through polyatomic ions, and we've been through covalent bonds. Okay, so make sure you guys go back into the assignment for today and find the link to your assignment. It is Thursday, April 2nd. So your assignment for today will be due tomorrow night at midnight or 11:59 p.m. So if you guys have any questions about that, let me know. Again, these notes should be on page 43 or 44. Let me go back and check. I had it right at the beginning of the video. But these should be in your interactive notebook. That list is still on Canvas. So if you go into your introduction module on Canvas, there is still a link to the Google Doc that has the list of your interactive notebook pages. So please make sure you're keeping up with that. If you guys have any questions, send me a remind, send me an email. Friday's assignment is just going to be to kind of check in with me and get on Zoom and make sure that you guys are having access to Canvas and that you have everything you need. But until then, keep working through these modules and these assignments, and I will talk to you guys soon. Bye.